Okay, so welcome to the lectures I'm going to give on chemical kinetic modeling for combustion. I owe a lot of what I know to a guy called Bill Pitts and Charlie Westbrook at Lawrence Livermore Lab. So I started off after my PhD. I did a postdoc there, and then I was a research scientist at the lab for 5 years. And most of what I know about chemical kinetic modeling, I learned from both of those guys, and I owe a lot of my knowledge to them. Today I'm going to talk about basic thermodynamic principles and the importance of the thermochemistry in chemical kinetic modeling. And then tomorrow I'll talk about basic kinetic principles deriving first, second order kinetic rate laws and so on. And then what experiments we use to validate chemical kinetic models, and what are the important features, how to simulate those reactors correctly, what are the important features that we're looking for in the data. And then I'll talk on day 3, talk about small species mechanism development. And then day 4, talk about large hydrocarbon mechanism development. And Professor Law kind of alluded to it. So, and I'll talk about this in the lectures, that, you know, when I worked in Livermore, I was asked by Charlie to develop mechanisms for N-heptane and isooctane. And they're very important fuels because they're the primary reference fuels. And even today, N-heptane is used oftentimes as a surrogate for diesel fuel, but also as a surrogate gasoline fuel. N-heptane, isooctane, and now toluene are typically used as surrogate to represent gasoline fuel. And so I was pretty much in the right place at the right time to develop mechanisms and reliable mechanisms for the primary reference fuels. Okay? And it's because of those mechanisms that I'm so well known in the field of combustion for chemical kinetic modeling. The point there that I want to make, so I developed, in those papers, I developed rate rules to generate the mechanism. So for instance, reaction class 1, unimolecular fuel decomposition. Reaction class 2, hydrogen atom abstraction from the fuel by different radicals. 3, alkyl radical decomposition, and so on. And at the time, we had 25 different classes of reactions, and then we had a rate rule that we applied to each class of reaction, which successfully simulated N-heptane and isooctane kinetics. But when I went back to Galway, one thing, and this is important, and it'll come up in the lecture, so it's just a general story to start with, and it'll be more specific later throughout the next 5 days. So, but when I was simulating N-heptane, and the model worked well, right? The mechanisms are developed in a hierarchical way. So we start with hydrogen. So we have a hydrocarbon. So you have to have a hydrogen mechanism. Then you have to have a CO mechanism. Then you have to have a methane mechanism, and so on, all the way up to C7 in the case of N-heptane, or C8 for isooctane. Okay. But if we wanted to simulate hydrogen or methane with the mechanism that I published for N-heptane, it actually wasn't that accurate, right? And that really bothered me, because the mechanism for hydrogen that you have there should accurately predict hydrogen if you then want to accurately predict N-heptane, right? So we kind of had the horse, or the cart in front of the horse, right? We had it backwards, okay? So when I came back I went back to Ireland, and what I wanted to do was to have a mechanism built from the ground up in a hierarchical way that I could be sure that, well, as sure as I could, that the chemistry was right, okay? So since then, so I moved back to Ireland in late 1999. You know, it was all talking about the millennium and Y2G ready and so on. Most of you guys were probably not born at that time, right? And so in the last 25 years, I've made it a large part. I still work on large mechanism development, but a large part of my focus has actually been on the smaller chemistry, because that matters actually. And in a lot of cases, the small chemistry is the controlling chemistry. And if you have accurate small species chemistry, you can predict a lot of the chemistry without necessarily having accurate large species chemistry. All right. So we've been working on the large species chemistry too. So published the N-heptane isooctane mechanism, and then I had a good PhD student. Her name was Emma Silken. She was around 2003, 2005. She graduated, and she went to work at Livermore. But when she was working with me, there were some developments that were subsequent to the N-heptane and isooctane mechanisms that we published, right? And there were new calculations of thermochemistry, there were new calculations of rate constants and for the rate rules. And in the mechanisms that I had developed particularly for isooctane, we had omitted to include potential reactions in the mechanisms, right? And when you then apply the rate rules with the new thermochemistry, new calculated rate rules from quantum chemistry, everything just fell asunder, right? And the mechanisms weren't that predictive, right? And it was really worrying to me. It was like, well, okay, do we really understand the chemistry, right? And then, so I was worried about that, but I had to park it because I had other projects to deal with and other things to do to deliver with students that I had at the time. But I always wanted to get back to it. And I got an opportunity to do that with a very good student who graduated in about 2015, 2016. His name was John Bugler. And he revisited all of this by looking at the pentane isomers, right? And I'll be talking about this in day 3, day 4, right? And he took, again, the latest thermochemistry, put in all the latest reactions and reaction classes, and we actually added about 7 or 8 more reaction classes to the 25 that we had, and it's now 32 or 33, right? And he was able to successfully then simulate the pentane isomers. But I was always in touch with people in the community, and there are some nice experiments being done by Craig Tejes and his group in Sandia labs, and we would get data from them too. And anyway, and actually the new rules and the new mechanisms match that new data much better than it did. So I could actually see, well, yes, the rate rules actually do work if you have accurate thermochemistry and accurate rate constants. And I think now, today, so subsequent to that then, I didn't have some kind of stopped again for a few years. And then I have a PhD student who's just defended his thesis last week with Heinz Pitch. And he, working with Mani Sarati's group at KAUST and Thomas Toriani's group, Tibor Nagy in, in Hungary, in Budapest, they looked again at using a code to optimize the thermochemistry and rate rules for all alkanes, not cycloalkanes, but N-alkanes and branched alkanes. And he's successfully done that. We haven't published that yet. So when Professor Law was saying you kind of wrap it up, we're kind of wrapping it up, right? And that's a nice body of work, but it's taken 30 years to wrap it up, right? Starting with the success of the primary reference fuel mechanisms that we published. But actually there were a lot of unknowns at the time. But the reason that they're so well cited was that they were better than nothing, right? I'm not saying that there was nothing out there, but they were the best state of the art that existed at that time. But there was still a lot of uncertainty in rate constants. The quantum chemistry calculations were only coming into their own. They were only starting when we were putting those mechanisms together. And the advancements have been much more significant since. So that's a sort of a synopsis, really, of the 5 days of lectures that I'm going to be giving you. right, in 15 minutes, all right? But that gives you the background of the material that I'm going to be covering. And I try to tell the story through the work that my PhD students have done, right? One thing you might be surprised to hear, and it's something I'm not entirely proud of, right, is that I haven't run a simulation in 15 years, right? So more and more I was a successful researcher, and then I became an administrator ultimately. Being a professor, you're writing grant proposals and you're orchestrating. And I don't know, Professor Law might agree with this or not, but it's a very uncomfortable period in that transition from being a researcher to becoming the orchestrator of the group. And it took me a long time. I'm not really a people person. I'm very honest. I'm not afraid to hurt people's feelings. Maybe it's a little bit of on the spectrum kind of thing. I think as a scientist, we are kind of all on a spectrum anyway. Anyway, now I'm more comfortable in that role, in the leadership role, and guiding people. But I've been lucky to work with really good people and good students, good postdocs. And it's nice when things work out, okay? So anyway, that's sort of the background.
Let me just add,
yeah.
When you get to my age, kind of old, then you gradually phase out being administrator and go back to your roots, do research.
Yeah.
Okay, that's what I'm doing now. And really fun, really fun. That's why it's important to get the fundamentals right. You get right now, get the fundamentals right. Because there's a certain period, all those parts you have to get involved. But then in the end, it's beautiful. Okay? Go back to the fundamentals. Yeah, I'm still publishing, I'm still working. I'm very happy. So.
Yeah. Yeah, anyway. Okay, so this is a diagram I like to use. So here I plot concentration on the y-axis versus time on the x-axis. So if you put species A into a tank, into a vessel, you close it, and you come along after any given time. There's no units here, so it can be arbitrary time units, right? What will happen is if nothing happens, then there's no reaction, right? But according to this equation, A can go to B, right? And then after a certain time, B can go back to A. So A is reacting to produce product B, right? So A decreases in concentration and time, and A decreases, and B increases in time. And then there comes a time, and it's about here. I use a dotted line or a dashed line for this. It's because it's a little bit of gray area, exactly. Well, not too gray. If you draw a vertical line here, you'll see precisely where equilibrium occurs, right? So, and at this state then, at this point, the rate of reaction of A to B and B to A reaches equilibrium, right? And so the rate of reaction is the same in the forward and reverse direction. So when we look at this diagram, typically we consider this part to be kinetics and this part to be equilibrium. All right? But there is no separation. If we look at this graph, there's no separation. So there's actually a link between kinetics and equilibrium. And I'll show you that link not today, but in the next lecture, or, during the week, okay? What that link is, okay? So if there's a link between kinetics and equilibrium, right, that link is thermodynamics. And so we need to have accurate thermodynamics if we're going to have kinetics going to equilibrium and being able to describe it correctly. All right. So the properties of interest then in thermodynamics are entropy, enthalpy, and heat capacity, either CP or CV. And these can be used for extrapolation, and I'll show you, to calculate then entropy and enthalpy. And then ultimately, we have a term called Gibbs free energy. So Gibbs free energy is enthalpy minus T times S, okay? So you've got this relationship between enthalpy and T times S. So what is Gibbs free energy, or can we make that tangible in a way? Because Gibbs free energy takes enthalpy and entropy together and puts it into one thermodynamic term, right? And then I'll show later, or I showed here, you've got log of the equilibrium constant is equal to minus delta G times RT. So if we have Gibbs free energy, we can actually then put that back into an equation where we relate it to the equilibrium constant, okay, KEQ, okay? So, but this Gibbs free energy takes enthalpy and entropy. So what is enthalpy and entropy, okay? You guys probably know better than me what that is, right? But I have a kind of a way of describing it in simple kind of children's way or layman's way. And it's this. So did you ever play Cowboys and Indians or Cops and Robbers when you were a kid on the street? I certainly did. I don't know whether your generation do, or play some sort of a game where somebody's chasing you and you're trying to get away, right? So, and one thing that helped me get away was if I jumped a wall, or I ran quickly at a wall and jumped over it. That actually inhibited the person behind me, and it helped me get away, okay? So that's what this Gibbs free energy term is. So if I stand here, right, and I want to go to the other side of the theater, or just the other side there, right, how do I get there? If I stand here and I do nothing, I have no entropy change, and H is 0, so actually Gibbs free energy is 0. And so no reaction is going to occur, right? Spontaneous reaction occurs when? Yeah, but sorry, like from a thermodynamic point of view, when does spontaneous reaction occur? Yeah, when Gibbs free energy is less than 0, delta G is less than 0. If delta G is less than 0, the reaction is spontaneous. Okay? So how do we get a delta G less than 0, or a G less than 0, right? Well, if we look at this term, if H is negative, how would H be negative? If we were at the top of a slope, right, and we were going downhill, right, H would be negative. How is H positive? H is positive if we have a positive slope, or if I want to go from here to the back of the theater, I have to climb up on the desk here, right? So this is an energy barrier. I have to put energy in to climb over this barrier here to get to the back of the theater, okay? Or in this line, I have to climb up on the chair to get to the door, right? So that's H, a barrier, okay? But if I'm on this trajectory and I only want to go to the chair, then H is 0, okay? It's flat, right? So H is 0, and then I have a minus T times S term, right? So the S term has to be positive if I'm spontaneously going to go from here to there, right? How is S positive if I move, if I become disordered? S is order, right? So positive disorder, positive entropy, if I move at all, I'm going to go to that wall. If I move very slowly, my S is very, very small, but it is positive, and I'm moving. But if I go fast, my entropy is bigger, and I go there quicker, right? So that's what G is equal to H minus TS is, right? So what makes that a most negative is if you have a 0 or negative H. In other words, picture you're on top of a hill and now you're going to go downhill, H will be negative, right? Or 0 if you're on a flat, right? And then entropy if you become disordered, right? And so Gibbs free energy would then be negative and the reaction will occur, okay? So this Gibbs free energy takes into account an energy barrier, enthalpy, and entropy, the disorder. It takes both of those two terms into account into one, right? And when you're a child playing cops and robbers or cowboys and Indians or whatever it was, and you were running from the guy behind you were actually using this equation, you didn't know it, right? This gives free energy. Because you jumped a wall or something, that was the energy barrier. The faster you ran at the wall, the easier it was to get over it, okay? And then, of course, the height of the wall. There'll come a height of a wall, no matter how fast you run at it, you won't be able to get over it, right? And then the Gibbs free energy becomes 0 or positive, and you can't get over it anymore, okay? So that's what Gibbs free energy is, in my layman's description of what it is, okay? So that's how I like to teach it, okay? And then chemical equilibrium, you take this delta G, and I'll show you how to do that later today or in the lectures, okay? But for the thermodynamics then, it gives you chemical insight into whether a reaction will happen or not, okay? As I just described, right? So is the reaction endothermic or exothermic? Will it be spontaneous or not? Okay, and if delta G is less than 0, then it'll be spontaneous. You can calculate what heat is released. What's the adiabatic flame temperature from the thermodynamic parameters? So it's very important that you're able to calculate them. Okay, and then this is as I said, John Bugler in his paper in 2015 revisited the thermochemistry of all the different species involved in a reaction. We'll come to this again, right? But here we have Gibbs free energy on the y-axis versus the reaction coordinate or the species involved in the reaction, okay? And what we calculated, based on the best thermochemistry we had at the time, that's 10 years ago now, was that relative to the thermochemistry that we were using, the latest thermochemistry said that our alkyl radicals should be lower in Gibbs free energy by 0.4 kilocalories per mole, relative to what we were using, okay? So just think about this for a second. And then the alkyl peroxy radical chemistry, I know but I want to talk about thermochemistry. We'll talk about the species tomorrow, okay? But for today, the alkyl peroxy chemistry. So what happens is we form an alkyl radical that adds to molecular oxygen, and you get this alkyl peroxy radical. And that thermochemistry increased on average by 1.4 kilocalories per mole. Okay, so basically what we had before was the alkyl radical was higher by 0.4 and the RO2 was lower by 1.4. Okay, so we'd say the well depth going from an alkyl radical to an RO2 radical was 1.8 kilocalories per mole deeper than it is now with the new thermochemistry. Does that make sense? Okay, so picture originally the R is up here, 0.4 kilocalories per mole. The RO2 is down here, 1.4 kilocalories per mole. The difference is going to be 1.8 kilocalories per mole, right? So if I have a reaction then that says R plus O2 gives RO2, right? That will reach an equilibrium, right? But the equilibrium originally was 1.8 kilocalories per mole Gibbs free energy units deeper than it is now, right? Or it's now 1.8 kilocalories per mole shallower than it was previously. If it's 1.8 kilocalories per mole shallower, what does that mean about the equilibrium of R plus O2 giving RO2? Will we have more R plus O2 or more RO2?
You can get more RO2. More RO2?
No, the wrong way around. Less, right? Because originally it was like this. So if you fall, think of it like this. You're starting off up here as R. You add to O2 and you fall into the well, right? And that well depth originally was 1.8 kilocalories per mole deeper, right? Now you have R, it adds to O2, it falls into the well, it's RO2, but now that well depth is 1.8 kilocalories per mole shallower than it was. So is it easier or harder to get back out of the hole? Easier, by 1.8 kilocalories per mole. So therefore, the system will tend to go more towards R plus O2 than it will to RO2, okay? Because it's easier to go back, okay? So that's why we have this red arrow, okay? So if we have R going to R plus O2 going to RO2, actually this equilibrium was shifted backwards by 1.8 kilocalories per mole, okay? Does that, hopefully that's clear to everybody, right? And now but say we're now RO2 and we have QOOH, okay? So this went up by 1.4, but this actually went up by 1.6. So there's actually a 0.2 kilocalorie per mole bigger barrier to the QOH species. So if I'm an RO2 species, we'll see what the QOH looks like again, don't worry about it. But if I want to generate a QOH species, the barrier to that species is in average 0.2 kilocalories per mole higher. So again, it doesn't want to, it's slightly harder to go to QOH by 0.2 kilocalories per mole. So that goes back, that arrow's pointing backwards, okay? So just by changing the thermochemistry, we're making the species stay as alkyl radicals rather than go forward to QOH radicals. Does that make sense? Okay, and then if you go to the QOH and you add O2, that well depth becomes shallower by 2.5 kilocalories per mole, right? Now, whether it's relative to this one or this one, I don't know, but it's either 2.5 or 2.3. But one way or another, it's shallower by 2.3 or to 2.5 kilocalories per mole than it was originally, right? So what's it going to do to the equilibrium? Again, it's going to drive it backwards towards QOH. So at low, I don't know if I don't have it. Okay, don't worry. So then we have QOH species, and now the QOH species is here, and the carbonyl hydroperoxide increases by 2 kilocalories per mole. So to form this species, this is actually in one step. So it actually goes forward by 2 kilocalories, or it makes it easier by 2 kilocalories per mole. Just trust me on that one. I know it's not consistent with what I said in the rest of them, but it is, okay? So by just looking at the thermochemistry though, and we have a system that can potentially be in equilibrium, well, just based on the thermochemistry of all the species, right? It's going to make the system generally less reactive than it was before, just based on the new thermochemistry. That's what we're learning from this, right? Okay, and that's part of the work that John did when we published this in 2015. Okay, so let me just show you then. So we had an original mechanism, and the original mechanism, so here the points here are experimental results. The black line is the model prediction, the original model prediction, and then the red line is the prediction when we include the new thermochemistry of the species in the model. Okay, and so the predictions change from the black line, which is slightly fast in comparison to the experimental data, to becoming too slow. Okay? So it changes the predictions by more than about a factor of 2, particularly in what we call this negative temperature coefficient regime. So if we look at it here, we're plotting, this is low temperature around 600 Kelvin. This is high temperature, you're talking about 1250, 1300 Kelvin down here, okay? And so if we're at low temperature and we increase the temperature, the reactivity increases significantly up to about 800 Kelvin. And then once we reach 800 Kelvin, the reactivity decreases until we reach 1000 Kelvin. And then if we get up to 1000 Kelvin, we go higher in temperature, the reactivity increases again. Okay? So this behavior is called negative temperature coefficient behavior because we increase the temperature, the reactivity actually decreases. Okay? So it's counterintuitive. Typically, we're told that you increase the temperature, the reactivity increases. Okay? But this is true for most alkanes. This kind of reactivity we observe all the time. Okay? And I'll explain why in the lectures. Right? So this was the effect of thermochemistry on the change. So thermochemistry is important to the kinetic predictions of the mechanism. Really, that's just the message. Okay. So enthalpy formation, enthalpy of formation is defined as the heat involved when 1 mole of a substance is produced from its elements in their standard state. Okay. And the standard enthalpy of formation of ammonia, we have a half a mole of N2 plus 1.5 moles of hydrogen gives 1 mole of ammonia. Okay? And conventionally, the standard enthalpy of elements is fixed at 0 kilojoules per mole at standard state. We have H2 for hydrogen, O2 for oxygen, and so on. It's 0. Okay. And then we have, of course, heat capacity. And we can write the heat capacity, first of all, heat capacity divided by the gas constant as the sum from n equal to 1 to n, so from 1 to n, whatever number, of a series of constants, okay, times t to the n minus 1, okay? So it's just a polynomial fit to accurately calculate the enthalpy as a function of temperature. Because oftentimes, I'll show it here maybe, I should have it here, apologies, but oftentimes the enthalpy, the heat capacity, as a function of temperature is very curved, right? So we need this polynomial fit to accurately capture it at any temperature, all right? So here's the heat capacity as a function of temperature. And you can see, like, we can't do this with 2 or 3 numbers, like the linear fit. It has to be a polynomial. Okay, so this is the polynomial that we use. Okay, so it's the sum of these these numbers times temperature to n minus 1. Okay, so and then enthalpy is the integral from T0 to T of the heat capacity at constant pressure times dt. Okay, so if it is, then the heat capacity over RT is equal to the sum from n equal to 1 to n of this polynomial species as well, okay, plus a times n plus 1 k over t, okay. Okay, so where a subscript n plus 1 at k times r is the standard heat of formation at 0k, but it is normally evaluated from the heat of formation at 298. Okay, so what do we do in, if we want to calculate entropy, you probably have been introduced this before, and what enthalpy is in terms of Cp and entropy in terms of Cp. So entropy is equal to the integral from 0 to T of Cp over T dt, okay? And then, so that's equal to this expansion, it's A1 log T plus the sum of these values. Okay, so this is evaluated from knowledge of the standard state entropy at 298 Kelvin. Okay, but we have codes, and one of the codes that we use in chemical kinetic modeling is Chemkin, right? So Chemkin uses is designed to use NASA polynomials, okay? And NASA polynomials use 14 values. So you have A1 to A7, and then you have another set of A1 to 7, okay, over 2 temperature ranges to accurately capture the heat capacity at any temperature. And from that, and if you know the enthalpy and entropy at 298 Kelvin, well, 298 and 300 Kelvin respectively, you can then calculate the enthalpy and entropy at any temperature. If you can calculate the enthalpy and entropy at any temperature, you can calculate the Gibbs free energy at any temperature. If you can calculate the Gibbs free energy at any temperature, you can then calculate the equilibrium constant at any temperature. And from the equilibrium constant, if you know the rate constant in one direction, you can calculate the rate constant in the other direction. Okay? So that's where the thermochemistry is all important. All right. So here we have Cp over R is the sum from n equal to 1 to n of A n times T to the n minus 1. Okay? And so if we expand this, we have Cp over R is equal to A1 plus A2 times T plus A3 times T squared plus A4 times T cubed plus A5 times T to the 4. Okay? So with 5 different parameter numbers, we can determine the heat capacity at any temperature, right? So, and then if we want to get enthalpy over R, okay, that's the integral of Cp over R dt, okay? And so if we integrate this here, the integral of A is AT, the integral of AT is AT squared all over 2. You've got A3 T cubed over 3, and so on. You have A5 times T5 over 5, plus a constant, which is A6. Okay? So here you integrate Cp over R dt, and you get the enthalpy. Okay? But now, actually, to get the enthalpy, we actually need 1, 2, 3, 4, 5, 6 numbers. Okay? Not just 5, we need 6. Okay? And then we have that again. And then, but if we want to get entropy, the entropy is the integral from 0 to T Cp over RT dt. Okay? And now, so we divide these values by T. Okay? So now we want to get the integral of A over T. Okay? And that's A times the log of T. Okay? We want to get the integral of A, which is A times T. Then we have the integral of A times, A3 times T, which is A3 times T squared over 2, and so on. So we have this, which we have A5 plus A5 times T to the 4 over 4, plus another constant, which is A7. Okay? So actually, as we see now, for Cp, we need 5 numbers. For enthalpy, we need a 6th, and for entropy, we need a 7th. So we actually need 7 numbers to accurately calculate Cp, enthalpy, and entropy as a function of temperature. Okay? And so the NASA polynomials, then, here's an example. We have 2. This is phenoxy. Okay, so, and we're going to use this code today. I asked you guys to download a code, and we'll use it. And you'll see, you'll get output, and it'll look something like this, okay? So here we have phenoxy. The thermochemistry was generated a long time ago using this code therm, right? It says there's 6 carbon atoms, 5 hydrogen atoms, 1 oxygen atom, and it's in the gas phase, right? And then it gives this number. So it has 300, it has 5,000, and it's 1404. So what does that mean? Okay, so well, let's just look at it for a second. We have 1, 2, 3, 4, 5, 6, 7. So this is a 1, 2, 3, 4, 5, 6, 7, right? But I have this in red. So they're the high temperature end fit for Cp, right? So, and from that you can get Cp, H, and S, right? As a function of temperature, from 1404 to 5000 Kelvin. Okay, so using these 7 parameters, I should say, you can accurately calculate enthalpy, entropy, and heat capacity from 1404 to 5000 Kelvin, right? And then with these other ones, 1, 2, 3, 4, 5, 6, 7, again, they're A1 to A7, but they're in the low temperature end. So you can calculate accurately CP, H, and S from 300 to 1404 Kelvin, okay? And then from using all 14, then you can accurately calculate it from 300 to 5000, okay? And here I have another one. This is dimethyl ether, CH3O, CH3 is dimethyl ether. Again, there's 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. It's in the gas phase. But now you can see that actually the range, again, it's 300 to 5000, but what do you call it? I forget now what it's called. There's a stop temperature or a link temperature. I don't know what I'm using the wrong term. It's 1364 Kelvin, okay? And so for the high temperature end, you use 1, 2, 3, 4, 5, 6, 7 values, and you can calculate it from 1364 to 5000. So this number, I forget what you call it, but this temperature changes from species to species. It's not always the same temperature, but it's around, that break temperature is around 1300, 1400 Kelvin, typically, okay? So if we move, next slide. Here then, I calculate, and I've done this, so I will ask you guys, please will you do the calculation, right? Calculate the heat capacity versus temperature for phenoxy radical. And you can see that the break temperature is, what was it, 1464, was it? Did I remember? 1404, okay? So the break temperature is 1404 Kelvin. But you should see that when you do the calculation over the whole range, that it should be seamless like this, right? And reproduce it for yourself to see that you can actually do it, okay? And see how it works. So just use an Excel spreadsheet to do that calculation, okay? Give it a go and see, right? So you can calculate heat capacity and you can calculate the enthalpy and entropy as well, okay? So you can do it. This is just, what you call it, the cycle, what you call this cycle for different species. Don't worry about it. But you can get the enthalpy. I'll show you this later in a later slide. So we typically get thermodynamic values from experimental sources, okay? And I'll give some examples of this as we're going through the lectures, okay? But also sometimes from quantum chemistry calculations, right? Or from theory, we can show that, well, theory is quantum chemistry calculation. Okay, so we have the enthalpy of formation is equal to the heat, which is equal to Cp dt. So Cp is the heat capacity at constant pressure of a compound. Okay, by integration, the enthalpy of formation of a compound at a temperature T is calculated by the change in enthalpy is equal to the change in enthalpy at 298 plus the integral from 298 to T of delta Cp dt. Okay, so that's equal to the heat of formation of 298 plus the integral from 298 to T of Cp of the molecule minus Cp of the elements times dt. Okay, so it's just saying you can derive the enthalpy at any temperature by knowing the enthalpy at 298 Kelvin and integrating for Cp dt, which is what we had already. Okay, and then entropy is equal to the heat all divided by T. So it's equal to Cp over T, okay, dt, Okay, so the contribution of entropy becomes important as temperature increases because you have the Gibbs free energy is equal to enthalpy minus T times entropy. Okay, so where do we get sources of thermochemical data then for combustion? Okay, there's no single compendium that contains all species, but you can use Benson's group additivity method, and we're going to do that later today, to determine, and the term code uses Benson's group additivity method to estimate or calculate thermodynamic parameters. Okay, there's the NIST webbook database. Okay, but this has stopped to be supported in the last number of years. It's no longer being supported. We have Thurgas, which is developed by Muller and Combe, but now it's Frédéric Blattman-Leclerc in France, in Nancy, maintains it. Okay, we have the third millennium ideal gas and condensed phase database for combustion. Okay, that was from Burkhardt and Goose. Okay, and that's available. The link is there, and we also have. Well, I'll show you in a minute. You can also get thermochemistry from quantum chemistry calculations now, and these are becoming more and more accurate as we go through the years. And then we can use statistical rate theory then to calculate rate constants based on the thermochemistry. Okay. So this is a very important source of thermochemistry which is maintained at Argonne National Laboratory. It's the active thermochemical tables, ATCT, okay? And that's the current benchmark for thermochemistry, even today in the combustion field, okay? It's constructed by solving an underlying thermochemical network. So it's Branko Rusick is the guy that maintains it at Argonne with other people, including Stephen Klippenstein, who does calculations to help support the network. But they've developed accurate, reliable, and internally consistent thermochemical tables of species. Okay. So many experimental measurements are considered, and both high-level ab initio calculations are combined with the ATCT approach in arriving at the recommended thermodynamic values that they provide. Okay. And they have very accurate heats of formation for about 350 carbon, nitrogen, and oxygen, hydrogen containing species, with uncertainties of the order of 1 to 1.5 kilojoules per mole. That's very high accuracy, I should say, sorry. So, and this represents very excellent progress for the combustion community. But the problem is that for kinetics, we need enthalpy and entropy, right? And if we only have enthalpy at 298, we need to be able to extrapolate to higher temperature, to combustion temperatures, right? Using the heat capacity, and then we can calculate entropy and enthalpy at any temperature, okay? So we need accurate entropy and heat capacity values so that we can get the Gibbs free energy and then for the equilibrium constant. So we can get accurate rate constants at any temperature for combustion, okay? So because of that, we need ways, if the active thermochemical tables only has the heats of formation and no entropy values, we're hooshed, right? So we need other ways to calculate those values, right? But what you can do is, if you're using another way to do the calculation, and you get a calculation of entropy, and you get the calculation of enthalpy, at least you can test the enthalpy that you've calculated against that which is in the active thermochemical tables to see that is actually consistent, okay? So at least that's a start, okay? And then there are automated computational thermochemistry values, codes now that are being calculated. So, for instance, Cacelli working with, this is a group basically in the Politecnico di Milano in Milan, and Stephen Klippenstein's group at Argonne, they published a paper which from the symposium in Dublin in 2018, 2019, where they used this automated thermochemistry, calculated thermochemistry values from a code, right? And that code is available now to do that automated calculation for you, right? Which is nice, right? But the thing is that there's a trade-off in accuracy between molecular size and accuracy of quantum chemistry calculations. So even if you have today, a lot of the models that I develop that we're looking at large hydrocarbons like C10, C12, C14, right? And even to this day, there's greater and greater uncertainty and quite high level of uncertainty in the thermodynamic parameters of species for even octanes, for C8 species. And the higher you go, the greater is the uncertainty in the thermodynamic parameters, okay? And then the greater the uncertainty in the rate constants that you're going to derive from those, right? So that's a problem, okay? So what we try to do, and I had a paper, I actually haven't cited it here, and probably I should have. My group published a few papers with Stephen Klippenstein in the last couple of years, where he did accurate calculations, or as accurate calculations as he could, for species up to C8, C9, right? And then we derived group additivity, group values, and updated group values based on his calculations to use then a code, a group additivity code, which I'm going to introduce to you, right, to calculate the thermodynamic parameters of species, okay? So let me just show you this, okay? So this is a group additivity method by Sid Benson. Let me introduce it now from the slide, and then we'll take a break, okay? Because it's getting up to 1 hour. Okay, so say we have this framework. We have a species A bonded to, a moiety, an atom A bonded to atom B, okay? And then there's three functional groups bonded to B and two functional groups bonded to A, right? So you've got 1, 2, 3, 4, 5, 6, 7 heavy atoms here, right? So what we do is so we have this molecule which has 7 heavy atoms. And what we do is we break down that molecule into groups which are defined by the environment of each heavy atom in the molecule, right? So this method of group additivity was pioneered by Sid Benson. There's a picture of him. He died in 2011. I don't know when this was taken, but it was in his later years in life, right? But so the nature of each atom in a molecule is considered, and the nature of each of their bonding partners, short-range effects, are also considered. And some long-range effects can be important, and they're also considered. So the molecule is split into its groups. Each group makes a contribution to the thermodynamic functions of the molecule. And if you sum all the contributions, you get the thermodynamics of the molecule. Okay? So I think at that, I'm going to stop. We'll take a break, and we'll come back at 3:15.